Welcome back to the deep dive. Today, we are tackling something that I think every data professional, every engineer, and honestly, anyone who has ever tried to open a file that was just a little bit too big for Excel has a real love-hate relationship with.
Oh, yeah, that is a very specific moment of panic.
You know the exact one I mean. You've written this local Python script, maybe you're using pandas, maybe it is just raw Python, and it runs absolutely perfectly on your sample CSV. I mean, the logic is flawless, the unit tests all pass, and you are feeling like an absolute genius.
And then you pointed at the production data set.
Exactly. You point at the new data set, which, happens to be 10 terabytes instead of 10 megabytes, and suddenly silence. Or you get a crash. Or the fan on your laptop spins up so hard, it sounds like it is literally about to take flight off your desk.
It is the absolute classic, well, it worked on my machine dilemma, but scaled up to a cluster crashing magnitude.
That is exactly the wall we are hitting today. And the ladder over that wall, for most of us living in the Python ecosystem anyway, means one thing: PySpark. But here's the thing, for everyone listening, we aren't just going to sit here and read through the documentation today. We are doing something a little bit different.
Right, we are combining sources.
Yeah, we are taking the official PySpark documentation from versions 3.2.1 all the way up to the bleeding edge 4.1.1, and we are smashing it together with this incredibly detailed, battle-tested list of senior-level engineering interview questions.
Which I think is a really powerful combination. Because, the documentation tells you what the tool can theoretically do. But those interview questions,
Yeah.
they reveal where the bodies are buried. They tell you what actually happens in a production environment when things go horribly wrong.
So that is our mission today. We are going to completely decode the PySpark ecosystem. We're going to figure out how you transition from pandas without losing your mind. We are going to look under the hood at memory management, which is the stuff they usually do not teach you in boot camps. And we are going to walk through specific high-stress question and answer scenarios, things like fraud detection pipelines.
Basically, think of this as a crash course
Yeah.
for the ambitious developer who wants to stop just writing scripts and start actually architecting systems.
I really love that distinction, scripting versus architecting. So let's just start with the landscape. If we look at the 3.2.1 and the recent 4.1.1 documentation, how are they actually defining PySpark these days? Because it feels to me like it is a lot more than just Spark for Python at this point.
It definitely is. I mean, at its core, yes, PySpark is the Python interface for Apache Spark. That is the textbook definition you will find. It allows you to perform real-time, large-scale data processing in a distributed environment. But the key insight here, and what really makes it sticky for engineering teams, is that it combines Python's learnability. The fact that almost anyone can pick up a Python script and intuitively understand the logic. It combines that with the raw, massive analytics power of Apache Spark.
Which is huge because historically, if you wanted that raw power, you were writing in Scala or Java. And that was a massive barrier to entry for a lot of data folks.
It was a huge barrier. You had data scientists who knew Python and statistics on one side of the room, and data engineers who knew Java and distributed systems on the other. And they literally could not talk to each other in the same code base.
They were speaking completely different languages.
Exactly. PySpark democratized that power. It supports Spark SQL, data frames, streaming, machine learning with MLlib, and Spark Core. But the real magic trick is that whether you are writing in Python or SQL, it uses the exact same underlying execution engine.
I want to pause on that point for a second because I think there is this lingering myth out there, and you hear it in interviews all the time, that PySpark is inherently slower than Scala Spark. Is that actually true?
Historically, yes, it was true. There used to be what we called a Python tax that involved serializing data back and forth between the Java virtual machine and the Python interpreter.
That sounds slow.
It was. But today, with the data frames API, absolutely not. When you write a data frame operation in Python now, it does not actually execute in Python.
Wait, what does it do then?
It gets translated into a logical plan, and that plan runs natively on the JVM, the Java virtual machine. So you aren't paying that Python tax anymore for using data frames. You are getting the performance of the native engine while just writing the comfortable, familiar syntax of Python.
That is huge. It basically means you can have your cake and eat it too. But speaking of comfortable syntax, I saw something really interesting in the docs about the Pandas API on Spark. Now, for someone who lives and breathes pandas, who maybe gets a little intimidated by the Spark syntax, this almost sounds too good to be true.
It is surprisingly robust. This actually used to be a completely separate project called Koalas, if anyone listening remembers that from a few years ago. But now it is fully integrated into PySpark.
So what does it actually do?
It is a total game changer for Python users.
Mm.
The promise, and the documentation is very clear on this, is that it allows you to scale your existing Pandas workloads without needing to learn a completely new API.
So hypothetically speaking, if I have a massive Panda script that keeps hitting memory errors on my local machine, I can just swap it out?
In many cases, yes, you literally just change the import statement. Instead of importing pandas as PD, you import PySpark.pandas as PS. The whole idea is having one code base.
Just one code base for everything.
Exactly. You can have code that works on small sample datasets using standard pandas for your local testing, and then that same code works on massively distributed datasets using the Pandas API on Spark. You switch contexts without any significant overhead. It bridges that gap between data analysis on a laptop and big data engineering on a cluster.
But I have to assume there are some caveats there, right? I mean, the Pandas inherently assumes all your data is sitting in memory on one single machine. Spark assumes your data is shattered everywhere across a network.
You are spot on. You do have to be careful, especially with things that rely on implicit ordering.
What do you mean by implicit ordering?
Well, in Pandas, row 5 always follows row 4. It is a single block of memory. In Spark, your data is distributed across 20 different machines. There is no such thing as row 4 unless you explicitly sort the data and assign an index. So while the API looks exactly the same to the developer, the physics happening underneath are fundamentally different.
Got it. So it is a bridge, but you still need to be aware that you are crossing a very wide river. Let's look at another moving part of the landscape here, streaming. I feel like there is a lot of confusion in the ecosystem because there are two different names floating around in the documentation.
You are very right to point that out. It is a common interview trap, actually. There is Spark streaming, and then there is structured streaming. This is a critical distinction for anyone building modern pipelines.
Okay, so what is the difference?
If you are looking at legacy systems or maybe reading tutorials from 5 or 6 years ago, you might see Spark streaming using something called D-streams. The documentation explicitly warns that this is a legacy project. It is no longer being actively updated with new features.
So the advice is just stay away.
Unless you are maintaining an old legacy system, yes, stay away. The modern standard is structured streaming. It is built directly on top of the Spark SQL engine. It is fault tolerant, it is highly scalable, and honestly, this is the coolest part. You express your streaming computation exactly the same way you express a batch computation.
Wait, really? The code looks the same.
Completely the same.
Yeah.
You just treat the real-time stream as a table that simply never stops growing. You append to it, you query it, exactly like a static data frame.
That simplifies things immensely. It means I don't need to learn a whole new mental paradigm just to handle real-time data. Now, before we get into the really deep internals, I have to ask you about this Spark Connect feature I saw highlighted in the 4.1.1 documentation. It mentions a client-server architecture. What does that actually mean for us as developers?
This is potentially the future of how we all interact with Spark. Traditionally, your driver application, the actual Python script running your main function, was somewhat heavy. It had to be very tightly coupled to the cluster it was running on.
Oh, I know. You needed the exact right Java versions, the exact right library dependencies on your local machine to match the cluster.
Exactly. It was a complete configuration nightmare. Pure dependency hell. Spark Connect fundamentally changes that architecture.
How so?
It allows remote connectivity to Spark clusters from literally any application. It effectively makes Spark a service. You can have a very lightweight client on your laptop, or even embedded in a web application, and it talks to a massive back-end Spark cluster seamlessly via gRPC.
So Spark basically becomes a database, or like a remote compute service.
That is exactly the right way to think about it. It makes Spark compute as a service. It decouples the client entirely from the backend, which is massive for improved stability and the overall developer experience. I mean, theoretically, you could run a PySpark script on an iPad that triggers a petabyte-scale job on an AWS server farm.
That is absolutely fascinating. It sounds like we are finally moving away from the dark days of managing heavy local configurations. But look, regardless of how we connect to the cluster, once our code actually hits those servers, we need to know what happens next. Which brings us perfectly to section 2 of our deep dive, architecture and internals.
The how.
Yes, the how. And this is where we really pivot into that interview prep material we gathered. Because in a senior level interview, or frankly during a 2 a.m. production crisis, just knowing the API syntax isn't enough. You need to know the actual mechanics. Let's start with a term I hear thrown around constantly, lazy evaluation. It sounds like the software is just slacking off.
It really does sound like that, doesn't it? But it actually means Spark is a procrastinator. but a very strategic one.
Walk me through that.
When you tell Spark to load a giant file and then filter it and then group it by a certain column, it does not actually do any of those things immediately. It just records your instructions. It builds a plan.
So it is basically just making a to-do list.
Precisely. It builds what we call a DAGI, a directed acyclic graph. And it just waits. It waits until you finally call an action.
What qualifies as an action?
Something like .count or .show or .write, a command that actually demands a result right now. Only then does Spark look at that entire graph of operations and figure out the absolute most efficient way to execute the whole thing together.
Okay, I get the mechanism, but why is waiting actually better? Why not just execute line by line like standard Python?
Because of optimization. Let's say you have a command to load a massive terabyte-sized file, and the very next line of code is a command to filter that data for just one single user, say user ID 100.
Okay, I follow.
If Spark wasn't lazy, it would load the entire terabyte into memory first, which might crash your cluster,
Okay.
and then it would filter it down to one user. That's a massive waste of resources. But because it is lazy, it looks at the whole plan and says, hey, I see you only want user 100. I can push this filter down directly to the storage layer. I am only going to read the specific lines from the disk that match user ID 100.
Oh, wow. So it literally saves you from reading data you don't even need.
Exactly. That is the raw power of the Catalyst Optimizer. It looks at your logical plan, and it literally rewrites your code to be better. It might push filters down, like we just said. It might reorder your joins to be more efficient. It does all the heavy analytical thinking for you.
That is incredibly smart. Now, what about this other term in the docs? Tungsten. It sounds like a heavy metal band or maybe a supervillain, but I know it is a core part of the Spark engine.
Tungsten was an initiative introduced to address the way hardware has changed over the last decade. It used to be that reading from the disk or network was always the slowest part of big data. But as networks got faster, CPU and memory efficiency actually became the new bottlenecks.
So how does tungsten fix that?
Tungsten manages memory explicitly. In a normal Java application, you rely on the Java garbage collector to clean up memory, which creates a lot of overhead. Tungsten bypasses a lot of that by laying out memory in a highly optimized binary format that actually mimics C++ dairy.
So it is basically hacking the JVM to run faster.
In a way, yes. It avoids the overhead of Java objects completely. And it also uses something called whole-stage code generation. It literally generates optimized raw byte code for your query execution on the fly. That is what makes modern Spark SQL run at bare metal speeds.
Okay, so we have this lazy, brilliant, highly optimized engine. But at the end of the day, this is distributed computing. Things break. Computers literally catch fire. Someone trips over a power cord in the data center. The classic interview question here is, what happens when an executor node suddenly dies in the middle of a job?
This is where the concept of lineage comes into play. You remember that DAG we talked about, the to-do list?
Right.
Spark keeps track of the lineage of every single transformation. It knows exactly that dataset C was created by filtering dataset B, which was created by loading dataset A.
So it has a complete family tree for every piece of data.
Exactly. So if an executor node suddenly dies and you lose a chunk of dataset C, Spark does not panic. It does not fail the whole job. It simply looks at the lineage graph and says, oh, I know exactly how this specific missing data was created. I just need to reread the specific part of dataset A and reapply the filter.
So it seamlessly reconstructs the lost data on a different node.
Yes. It recomputes only what is actively missing. It does not have to restart the entire massive job from scratch. That is the very essence of fault tolerance in Spark. It intelligently trades computation time for extreme reliability.
That is incredibly clever. But of course, it relies on that underlying plan being sound. Which brings us to the core debate I see outlined in the documentation. RDDs versus data frames. I feel like there are still some old school purists out there who just love using raw RDDs.
And the expert advice here, especially for anyone going into an interview, is very, very firm. Do not fall into that trap. RDDs, which stands for Resilient Distributed Datasets, are the low-level assembly language of Spark.
But they are powerful, right?
They are powerful, yes, you can do anything with them, but they are completely opaque to the Spark engine.
Opaque in what way?
When you use a custom Python Lambda function inside an RDD operation, the Spark engine has absolutely no idea what you are doing inside that function. It just sees a black box of Python code. So it cannot optimize it, it cannot rearrange it, it just has to execute it blindly.
So you completely lose the Catalyst optimizer. You lose all that smart filtering we just talked about.
Completely. You lose Catalyst, you lose Tungsten, you lose all the modern advancements. The documentation explicitly advises using data frames because they allow Spark to understand the actual intent of your query. This lets Spark automatically construct the most efficient query plan possible. If you stick to RDDs, you're basically manually driving a manual transmission car. If you use data frames, you have a professional race car driver behind the wheel.
I will definitely take the professional race car driver, thank you very much. But even with a race car driver, you can still run out of gas, or in our case, run out of memory. This moves us nicely into Section 3, memory, performance, and the dreaded shuffle.
These are the silent killers of Spark performance.
Let's tackle memory management first. The source material draws a very hard distinction between execution memory and storage memory. Why does that distinction actually matter to a developer?
Think of it like your own brain. You have memory that is reserved for memorizing static facts. That is storage memory. In Spark, that is used when you explicitly cache a data frame so you can read it again later quickly.
Right.
But then you also have memory reserved for doing active calculations right now, doing math in your head. That is execution memory. Spark uses that for doing shuffles, complex joins, sorting data, and aggregations.
And do they share the same physical pool of RAM on the server?
They do. They share a unified region, and they can dynamically borrow space from each other. But there's a massive tension there. If you forcefully cache too much data, using up all your storage memory, you leave absolutely no room for the engine to actually perform the calculations. You starve the execution memory.
And what happens when you run out of execution memory in the middle of a big join?
You experience what we call a spill to disk.
Spill to disk. That sounds expensive.
It is the ultimate penalty box. When the data being processed does not fit in the available RAM, Spark has to pause, write those temporary files out to the physical hard drive, and then read them back later. Physical disk I/O is orders of magnitude slower than RAM.
So your job just grinds to a halt.
Completely. If you are constantly spilling to disk, your job performance falls right off a cliff. You will look at the logs and see individual tasks taking minutes instead of milliseconds.
And what about garbage collection? You mentioned earlier that Tungsten tries to avoid it, but PySpark is still technically running a Java process under the hood, right?
Yes, exactly. In PySpark, you still have the JVM running on the worker nodes. If you write poorly optimized code that creates millions of tiny temporary objects, the Java garbage collector eventually has to freeze all execution to sweep through and clean them up.
This is what the docs call GC pressure.
Yes. High GC pressure can cause your application to randomly hang, or if the pauses get too long, the nodes might stop responding entirely and the whole cluster can crash.
Okay, now let's talk about the main villain I mentioned earlier, the shuffle. The classic interview diagnostic question here is twofold. What actually causes a shuffle, and how do you reduce the cost of a shuffle?
A shuffle happens when data physically needs to move across the network between different worker nodes. This almost always occurs during operations like a group B, a join, or a repartition command.
Give me a visual for that.
Imagine you are trying to sort a massive deck of playing cards, but those cards are randomly spread across 10 different rooms in a building. You have to physically run around the building, moving cards between rooms, just to get all the aces into one pile. That is a shuffle.
And moving things between rooms involves network latency, disk I/O, serialization overhead.
Everything you absolutely want to avoid in a distributed system is by far the most expensive operation in Spark.
So how do we actually reduce it? The source material mentions something called broadcasting.
Broadcasting is a truly beautiful optimization, specifically for joins. Suppose you have a massive 10 terabyte table of user transactions, and you need to join it with a tiny lookup table of store zip codes, which is maybe only 500 kilobytes.
Okay, a huge table and a tiny table.
Normally, Spark would try to shuffle both tables across the network to match up the keys. But instead of shuffling the massive transaction table, which means moving 10 terabytes of data over the network, Spark takes the tiny store code table, sends a full copy of it to every single worker node, and just keeps it pinned in memory.
Oh, I see. So the big data never actually has to move.
Exactly. The big data stays put on its original nodes. The small data does all the traveling, that is called a broadcast join. It completely eliminates the network shuffle for the large table.
But there is a catch, right? There is a trap here. The interview question asks, what happens when the broadcast threshold is exceeded?
The trap is when that small table isn't actually small. Let's say it is a 10 gigabyte table, and you force Spark to broadcast it. Spark tries to send 10 gigabytes to every single node. If that exceeds the available memory on the executor, or if it just creates massive GC pressure trying to load it, you instantly crash the executors.
You just get a massive out-of-memory error across the board.
Right. You have to be very, very careful that your broadcast variable actually fits comfortably in memory. It is a high-risk, high-reward optimization.
Okay, so we have covered the engine, we have covered the memory fuel, we know what causes the crashes. Now let's actually drive the car. I want to throw some of these specific engineering coding problems from the interview list directly at you, because I think these applied logic scenarios are what really separate the junior developers from the senior architects.
Let's do it. These are honestly my favorite part because they test if you can actually think in distributed terms rather than just writing a script.
First scenario up is about data quality, specifically deduplication. So the scenario is this. You have a real-time stream of transactions coming in. But because of network retries from the upstream API, you have duplicate records. You need to keep only the latest status for every single transaction ID. How do you handle that in PySpark?
So a junior engineer looking at that might just run a simple .distinct command.
Why is that the wrong answer?
Because .distinct only removes rows where every single column is exactly identical. In a real-world transaction system, you might have two rows with the exact same transaction ID, but one arrived at 1:0 p.m. and says pending, and the second one arrived at 1:05 p.m. and says complete.
Ah, so .distinct would just keep both of them because the timestamp and status columns are different.
Exactly. Now you have bad data. You need the logic to explicitly say, look at all the rows for this ID and keep the one with the most recent timestamp.
So how do you actually write that?
You use a window function. This is standard SQL logic applied to Spark. You partition the data by the transaction ID, you order it by the timestamp in descending order, and then you apply a row number function. Then you simply filter your data frame to select only the rows where the row number equals 1.
Right, so you are logically grouping the entire history of each transaction together, sorting it, and just picking the winner.
Correct. But here is the senior level nuance that the interviewer is waiting for. This operation can become incredibly expensive if you have a massive historical data set. If you are doing this in a continuous streaming context, you cannot keep all that history in memory forever. You have to use something called watermarking.
Watermarking, what does that do?
It tells the Spark engine, only keep the state for transactions that arrive within the last 10 minutes. If a duplicate arrives an hour late, just drop it. Without a watermark, your state store grows infinitely until it crashes the whole system.
That is exactly the kind of production detail we are looking for. Okay, next scenario, stew. We touched on this, but it is a major bottleneck. The interview question is simple. How do you detect skewed keys in your data set?
Data skew is simply when one partition of your data has, say, 90% of the records, and the other partitions have almost nothing. Imagine you are processing a massive feed of Twitter data, and you group it by user.
Okay.
The worker node that gets assigned to process Justin Bieber's tweets is going to be grinding away for hours. Meanwhile, the worker node assigned to process my tweets finishes in about 2 milliseconds and then just sits there doing nothing.
And in Spark, a stage is only as fast as its slowest task, right?
Exactly. The whole job waits for the Justin Bieber node to finish. To detect this, you don't just guess. You run a quick aggregation on your join keys before you do the heavy processing. You count the number of records per key and sort descending. If your top key has 50 million records and the median key has 10, you have massive skew.
Okay, so you found it. How do you fix it? The notes here mention salting.
Yes, you have to salt the keys.
Salt the keys, like you are cooking.
Very similar concept, actually. You append a random number to the end of the highly skewed key. So instead of all the records just having the key Justin Bieber, you use a random function to assign them keys like Justin Bieber _1, Justin Bieber _2, all the way up to, say, 100.
Oh, I see.
By adding that random salt, you artificially break that one massive pile of data up into 100 smaller chunks. Now, those chunks can be distributed evenly across 100 different worker nodes to process in parallel. Once the heavy lifting is done, you strip the salt off and aggregate the final result back together.
That is a brilliant trick. It forces the distribution. What about this next one? Missing data. What are the strategies for handling columns that are extremely heavy with null values?
This usually depends on the specific business logic, but mechanically, you have a few options. You could use .fill nulla to replace them or .dropna to just throw the rows away. But purely from an efficiency standpoint, if a column is mostly null and you are using a modern columnar storage format like Parquet, which Spark is heavily optimized for, those nulls are actually very, very cheap to store. They compress beautifully.
So storing them isn't the issue.
No, the massive problem arises if you try to perform a join on a column that is full of nulls.
Let me guess, because all the null values get hashed to the exact same partition.
Bingo. You instantly create a massive skew problem.
Mm-hmm.
If you try to join two tables on a key column that happens to be 50% null, all of those millions of null records get routed to one single node, and it will crash. You almost always want to explicitly filter out the nulls before you perform the join, or assign them a synthetic random value so they distribute evenly across the cluster.
That is a massive pro tip for anyone listening. Do not join on nulls. All right, let's move to time and window functions. These always seem to trip people up. The scenario is sessionization. How do you implement logic that groups events into sessions, like, say, defining a session by a 30-minute gap of inactivity?
This is a notoriously hard problem in distributed computing because a session isn't a fixed block of time like a day or an hour. It is completely dynamic. It is defined solely by inactivity.
Right, if I click a button right now and then I click again 29 minutes later, the session continues. But if I wait 31 minutes, it is a brand new session.
Exactly. In standard Python, you would just loop through the records and keep a running timer. But you can't do a simple loop in distributed PySpark. So you use a combination of window functions, specifically a lag function.
How does that work step by step?
First, you partition the data by the user ID and sort all their events chronologically. Then you use the lag function to look at the row immediately preceding the current row. You calculate the time difference between the current event's timestamp and the previous event's timestamp.
Okay, you find the gap.
Right. If that gap is greater than 30 minutes, you create a new column and flag it with a 1, meaning this is a new session start. If the gap is less than 30 minutes, you flag it with a 0.
And then how do you group them?
Then you do a cumulative sum over those ones and nears. Every time a new session starts, the sum increments by 1. That running sum effectively becomes your unique session ID for that block of events.
Wow, that is incredibly elegant, using a cumulative sum of the flags to generate an ID. I love that. Let's do another time-based one, rolling windows. Say the business wants a rolling 7-day transaction sum for every user.
That is a standard window function again. You partition by the user and you order by the date. But the critical interview trap here is understanding the frame specification. Specifically, knowing the difference between rows between and range between.
What is the exact difference?
If you use rows between, it looks at physical rows in the data frame, so the last 7 rows. If a user makes 5 transactions in one day, rows between is going to give you a very weird, inaccurate sum.
Because it's counting rows, not time.
Yes, exactly. Range between, on the other hand, evaluates the actual value of the sort column. So it looks back at the last 7 days based on the timestamp, regardless of how many physical rows exist in that time frame. For time series analysis, you almost always want to use range between, especially because you might have missing days where the user did nothing. Spark maintains a sliding state window in memory to calculate this efficiently as it processes the sorted data.
Okay, one more applied scenario before we move into the production architecture section. Churn and fraud. Let's say detecting a specific fraud pattern, like a user making 3 transactions within a tight 10-minute window.
This is very similar to the sessionization logic, but it is strictly time-bound. You could theoretically do a self-join, where you join the table to itself to compare times, but that creates a massive explosion of data and is horribly inefficient.
So what is the better way?
Again, the window function. You create a window partitioned by the user, ordered by time, and using range between to look back exactly 10 minutes. For every single transaction, you simply count how many other transactions exist within that sliding 10-minute window. If the count is greater than or equal to 3, you flag the row as potential fraud.
It really sounds like window functions are just the absolute Swiss Army knife for all of these complex logic problems.
They absolutely are. If you want to pass a senior data engineering interview, or if you just want to write efficient PySpark code, you have to master window functions. They come up in almost every single complex analytical requirement.
Duly noted for everyone listening. Okay, let's graduate. We have written the logic, the unit tests pass, the Spark UI looks clean. Now we actually need to deploy this pipeline into the real world and keep it alive. This is Section 5, Senior Level Production and Delta Lake.
Welcome to the real world, where things break constantly.
Exactly. The source material brings up Delta Lake almost immediately as a solution for enforcing ACID guarantees. First off, why are ACID guarantees so critical in a distributed system? I mean, standard databases have had this for decades.
Because distributed systems are inherently messy. Imagine you have a Spark job, writing a terabyte of data to a cloud storage bucket. Halfway through the job, the cluster loses power.
The job fails.
It fails. But without ACID guarantees, atomicity, consistency, isolation, durability, That failed job might leave you with 500 gigabytes of half-written, corrupted, useless data sitting in your production bucket. Your downstream dashboards will read it and show complete garbage.
Just a partial mess.
Right. Delta Lake brings standard database transaction logs to your data lake. It ensures atomicity. It guarantees that either the entire write operation completely succeeds or it completely fails and rolls back. You never get a partial mess.
And it also solves this thing called the small file problem. I see the specific commands optimize and Zorter highlighted heavily in the outline.
Yes. The small file problem is rampant in streaming. If you are constantly streaming real-time data into a data lake, you are creating thousands or millions of tiny little files, maybe just a few kilobytes each.
Why is that bad?
Because every time Spark tries to read a file, there's metadata overhead. If it has to read a million tiny files, it spends all its time just opening and closing file headers, and it crawls to a halt.
It's like trying to read a novel where every single word is written on a separate sticky note.
That is the perfect analogy. It is a nightmare for the reader. Delta Lake provides a command called optimize. It acts like a background maintenance job, does all those millions of sticky notes, and efficiently rewrites them into proper, large, optimally sized files.
And what does Zorter do?
Zorter is an extra layer of optimization. While it is rewriting those large files, it physically sorts the data inside them so that similar data sits close together on the disk. For example, sorting by date and customer ID.
How does that help?
It allows for massive data skipping. If a query only asks for data from yesterday, Spark can look at the file metadata and realize it can completely skip reading 99% of the files, because Zorter guaranteed that yesterday's data is isolated in one specific block. It makes your queries lightning fast.
Okay, let's talk about governance. The docs mention the bronze, silver, gold architecture. This seems to be the absolute standard now, right?
It is the defining industry standard pattern for building modern data lakes. It is all about progressive refinement.
Break those layers down for me.
Sure. You start with bronze. This is the raw ingestion layer. You just get the data into the lake exactly as it arrived from the source. You don't filter it. You don't cast types. If it is a messy JSON blob, you save it as a messy JSON blob.
Why not clean it immediately?
Because if you make a mistake in your cleaning logic, you want to be able to go back to the original raw data to fix it. If you throw the raw data away, it's gone.
That makes total sense. So what is silver?
Silver is the cleaned, filtered, and augmented layer. This is where your heavy PySpark jobs run. You cast your dates properly, you handle the nulls we talked about, you deduplicate the records. This creates a trusted, enterprise-wide source of truth.
And finally, gold.
Gold is your business-level aggregates. These are the highly refined, aggregated tables built specifically for reporting. The daily sales KPIs, the churn models, they're pre-calculated and ready for a BI tool or an executive dashboard to consume instantly.
And how does schema governance fit into this? I mean, upstream sources change columns all the time without telling anyone.
This is another place Delta Lake shines. It enforces schema on write. If an upstream API suddenly changes a critical user ID column from an integer to a string, a standard data lake might just blindly accept it and corrupt your downstream pipelines. Delta will detect the mismatch, throw an immediate error, and stop the write process, protecting the integrity of your silver and gold tables.
It's basically a bouncer at the door checking IDs.
Okay, now for a very practical, boots-on-the-ground question from the interview list. Your daily Spark job latency suddenly increases by 300%. What is the absolute first diagnostic step you take? You do not guess, and you do not blindly add more server nodes. You open the Spark UI.
The Spark UI, the dashboard.
Yes, it is the absolute source of truth for the cluster. You go straight to the Stages tab. You look for the specific stage that is taking 90% of the total time. Once you find it, you drill down into the individual tasks inside that stage.
What exactly are you looking for in there?
You're looking for anomalies. Is there one single task that is taking 45 minutes while all the other 199 tasks finished in 10 seconds? If so, you have identified data skew. Are you seeing massive amounts of data in the shuffle read or shuffle write columns? That means you have a network congestion problem due to a bad join.
What if everything is just generally slow?
Then you check the GC time column. If your tasks are spending 40% of their time in garbage collection, it means your workers are completely memory starved. And you either need to allocate more RAM or optimize your code to create fewer objects. The UI tells you exactly where the bottleneck is.
If you know how to read it.
Exactly. It visualizes the entire DAG we talked about earlier and gives you the timeline of every single task.
Yeah.
It is your best friend in a crisis.
What about reliability and deployments? The outline mentions CI/CD for Spark, continuous integration and deployment. How do you actually manage that for big data?
You have to start treating your Spark code exactly like traditional application backend code. It lives in a version control system like Git. You run automated unit tests against it on every pull request.
Using that Pandas API or a local Spark session like we discussed?
Precisely. And for deployment, you must package your dependencies properly. The biggest amateur mistake is just running pip install commands on the fly during a production job initialization.
Because the PyPI servers might be down or a library version might update overnight and break everything.
Exactly. You want deterministic builds. You should use Docker containers or pre-built virtual environments to ensure that the exact environment you tested in staging is identical to the one running in production.
Makes sense. Now, another big buzzword that comes up a lot, idempotency. The question asks about designing idempotent pipelines. What does that actually mean in practice?
Idempotency is a fancy word for a very simple critical concept. If I run the exact same data pipeline job twice, I should get the exact same final result. I should not get duplicate data.
Right.
In PySpark and Delta, you typically achieve idempotency by using merge operations instead of simple append operations. Your code should explicitly say, look at the target table. If this transaction ID already exists, update the status. If it does not exist, insert it.
Because if you just use .append and your scheduler accidentally triggers the job twice.
You instantly double your company's reported revenue for the day, which is generally considered a resume-generating event if you do it to the financial reports.
Yeah, that will definitely get you fired.
Exactly. Always designed for idempotency. Assume your jobs will randomly restart.
Finally, the last production topic, workload isolation and cost optimization. The notes specifically mention this regarding cloud services like AWS EMR or Databricks.
This is an architectural rule. Do not run your massive, heavy, automated ETL jobs on the exact same cluster that your interactive data science team is using for ad hoc queries.
Why not?
Because the heavy batch jobs will hog all the CPU and memory, and the data scientists will complain that their simple queries are taking 10 minutes to run. You have to physically isolate those workloads onto separate clusters.
And how does that relate to cost optimization?
Because once you isolate the workloads, you can tune the hardware. For your automated batch jobs, you can use spot instances or preemptible VMs on Google Cloud. These are excess servers the cloud provider sells at a massive discount, sometimes 80% off.
But the catch is they can take them away from you at any second, right?
Yes, they can just terminate the server with a 2-minute warning. But remember what we learned about Spark's fault tolerance.
The lineage.
Exactly. Because Spark tracks lineage and is perfectly fault tolerant, if a cheap spot node suddenly disappears, Spark doesn't care. It just seamlessly retries the failed tasks on a surviving node. So you leverage the software architecture of Spark to dramatically reduce your cloud bill.
It all completely connects back to the core architecture. The fault tolerance isn't just for avoiding crashes. It literally allows you to save millions of dollars on compute costs.
That is exactly right. That is thinking like an architect.
Wow. Okay, let's take a collective breath here. We have covered an absolute mountain of ground today.
We really, really have.
I mean, we started with the definition of PySpark as this powerful bridge between the readability of Python and the raw horsepower of the JVM. We looked at the modules, SQL data frames, the new Pandas API, structured streaming. We totally tore apart the internal architecture, lazy evaluation, the DAG, the Catalyst optimizer, Tungsten.
We faced the demons of memory management and the dreaded network shuffle.
We did, and we solved real practical coding problems. Deduplication, handling skew with salting, sessionization using window functions, and then we ended with the high-level architecture of Delta Lake, medallion architectures, and production reliability.
It is a full, comprehensive journey from writing your first Hello World script to operating as a senior data architect.
So, after all of that, if you had to boil this entire deep dive down into one thing, what is the absolute final takeaway for the listener today?
The main takeaway is this. Just knowing the syntax of PySpark, knowing how to type .filter or .groupb is simply not enough. That is the easy part. True mastery, the kind of mastery that lets you handle terabytes of data without getting paged at 3 a.m., comes from deeply understanding the internals. You have to understand how memory is partitioned. You have to understand lineage. You have to understand what triggers a shuffle. You have to respect the physical constraints of the distributed system. If you treat PySpark like a magical black box that just makes your Pandas code run faster, it will eventually crush you in production. But if you actually understand how the engine thinks, You can make it do incredible, highly efficient things.
That is a very powerful summary. And honestly, I have one more thought to leave everyone with before we go. It goes back to that Spark Connect feature we touched on briefly from the newest 4.1.1 documentation.
The client-server model.
Yeah. If Spark is really moving toward a model where it can just be used as a service remotely from literally any application, a web app, a mobile phone, a lightweight Python script on your local machine, does this signal the end of the traditional heavy data engineer?
That is a very provocative question.
I mean, are we inevitably moving toward a world where complex data processing is purely remote, entirely decoupled, and maybe even totally serverless from the developer's perspective?
It definitely lowers the barrier to entry even further than PySpark already did. It might honestly mean that in 5 or 10 years, the act of configuring a Spark cluster will be a completely lost art, much like wiring a physical server rack is today. We might just be purely consuming compute as a service without ever thinking about the nodes.
That is definitely something to mull over. For now, though, I highly encourage you, the listener, to pick just one pain point we discussed today. Maybe it's data skew, maybe it's garbage collection pressure, or maybe it's just looking for long-running tasks. Go look at your own pipelines tomorrow morning. Open up that Spark UI, dig into the Stages tab, and see what you actually find.
You might be very surprised at what is lurking in those tasks.
Thanks for diving in so deeply with us today. We will see you all on the next one.
Happy coding, everyone.